that we've experienced because of that. I guess quite a technical algorithm and how it works, and kind of show you the benefit. I'll skip over the introduction. I'll go very quickly over the introduction. We'll then get into why it matters, what the challenges are, why haven't we done it today? That really technical deep dive into how the algorithm works from a real data science perspective, and then hopefully we have some time at the end for some answers. So introduction, who are Thales? Hopefully everybody's kind of heard of Thales on the webinar. I'll go very quickly over this. Thales has been in the rail industry since 1950s, and every year there's over 8 billion public journeys. So the numbers are 250,000, 140 different metro lines. So this really, I guess, gives us and the domain expertise that is required to really optimize maintenance and produce a smart maintenance. Next start, why is smart maintenance important? We carried out a study and we found that aside from external events, or events that you could never predict, never prevent, so trespassers on the line, for example, or weather storms, signalling was actually second in line at 16% of the unplanned shutdowns. Now, that's clearly for us target. That's something that we can do something about, something that we can actually start to improve. 16% into a monetary value, our research has shown that companies worldwide can be saving as much as £149 million with those unplanned. This was, how do we sustainably reduce downs? How do we make a real impact and do it over a long period of time? And that's what we're going to answer over the next few minutes. The different maintenance strategies that we tend to see across the rail industry today. If we start off at the very left with the dinosaur, we've effectively got the fault repair only. So this is where you use a piece of equipment, you never go out and touch it, and then eventually it breaks and you just either replace it or repair it. It's the very basic, it's the kind of fire and forget strategy of I'm just going to keep using it until it's it. We rarely see that nowadays. I think a lot of organisations have moved up this stack. Second tier there being, so every now and again you'll maybe go down and inspect the asset or the device, and you'll probably service it, maybe change some. Next level up is basically the same but done on a schedule, and that's really what we call preventive maintenance. So every 2 months you may re-grease a slide share. It may not need doing, but the preventive maintenance schedule says do it anyway, because that's what our experience has learned. And we see a lot of potential for cost optimization in preventive, a smart maintenance tool such as the one that Thales have designed. Where we're at today, condition monitoring, so proactive maintenance, health assessment, diagnosis. So basically what is happening now and what actions do I need to happen now? And then where we hoped is around forecasting and intelligent assets. So really look to say, I understand what's happening now, but what might happen in a week, what might happen in a month's time. Intelligent assets, kind of actionable recommendations. So this part needs changing in 2 months, and we can start to plan and optimize our maintenance around that. So how do we shift towards that smart maintenance strategy? Now, Tyrus, which is the Thales smart maintenance platform. When we talk about Tyrus, we talk about Tyrus in 3 different categories. We talk about discover, predict, and advise. Now, discover is all about connecting your assets to the system. It's about being able to collect that data and visualize that data efficiently. So at this point, behavior of that particular point machine or a track circuit or an axle counter, you're learning about what it does and how it works. That's what we call our discover phase. You've got that understanding of the asset behavior, you can move into predict, where you start to leverage that knowledge to provide predictive algorithms that basically it takes the human out of the loop and provides that context and that understanding. Advise, this is really where we take a holistic view of work and we start to really optimize. instead of maybe the system popping up and saying you've got a predicted failure on your point machine in 3 weeks' time, say you've got this failure in 3 weeks, have this team available that can fix it, they have the right qualification, links all of that together for you and provides some action. Today we're going to be talking about the predict element and how we've implemented that. So about point machines, Tyrus isn't limited to just point machines. We also cover counters through the Thales. We cover CBTC, which probably isn't of interest today, through the Thales cell track system, interlocking through and a wide variety of track circuits as well. And the benefits of monitoring those we see across the bottom there. We see from early awareness, so being able to give the operator or the maintainer a bit of a heads up to say that this asset is deviating away from its normal behavior, through to not having to do the same manual tasks over and over and really boosting productivity of the workforce, all the way through to real-time assistance. Now this one actually is most effective, especially through COVID times, and what we're talking about here is allowing our customers to pick up the phone and basically look at the same data our experts in Thales. So maybe one of our engineers are dealing with a really problem on a point machine. Our experts can dial in data and kind of share some of that expert knowledge. So this really helps to reduce time to resolve some really complex faults. Tyrus, let's look at some of the challenges of actually achieving that value from remote condition monitoring. Now, when we talk about notifications off asset performance, you can see on the diagram on the left scale of that detection criteria. To the left, you introduce a lot of false alarms, including more of that noise. If you go too far to the right, reducing the signals, so you're potentially missing alarms. Now, trying to achieve a balance in that is really difficult, and use of the data plots on the right-hand side there. They are 4 different point movements machines. See visually the amount of variability within those traces. Left, which is a very flat movement, the top right, which has a more accentuated locking phase, a HPSS point machine in the bottom right, which is power that's very different again, and then one at the bottom right there, which has a really extended movement phase. So the amount of variability is huge between the different point machines, and this is why it's so difficult solution that just the point machines. A bit more detail, there's 3 case studies that I can talk through very quickly. Just being the symptoms. So if we just look at stalled moves, so where the point machine has tried to move and something's blocked its way, so it's stalled. 3 different types of point machines, and you can see 3 different, very different symptoms being presented there as well. So how is your algorithm ever going to be able to understand that? And when you look at that, how do you even know what to tell the on-site team at this point? It's to be an expert in these. The environment can play a huge part. If we look on the left, we can see one type of power. For instance, it's quite a linear correlation, so maybe we could tune the algorithm around that. But then we look at a different point machine on the right there, and we can see that it isn't a linear relationship anymore. It's quite a complex relationship. And as the temperature changes, the power. And the third case there, if we just look at that period across a year, changes seasonality a lot. So the left-hand side is the raw data, the right-hand side, the reduced. And what you can see, the red line going up is the trend for increasing, noisy and so convoluted. So even over very long periods of time, we've seen some differences. We've seen more variability within this data that is very difficult to account for. So with that as a problem, and then the new algorithm that we're going to be introducing. So let's have a look at some real data. This is all real data that's come from real point machines, from some of our anonymized. Now, the feature plot that we've got there, you can see lots of variation between the green and the purplish dots. Now, variability between different types of point machines. We even get variability down to different movements. Point machine moving one way and the purple is the point machine moving the other. And you can already start to see some huge variability there between, so we really have to focus down a really accurate view. Now, how is this done currently? How do we see this being done today? What tends organizations will look at the data, look for some within that data. So if we take this example here, looking at this and saying, right, we've got a peak at the end, and we've got a longer swing duration than usual as well. So maybe we'll create a feature around that and we'll monitor that as well. When we look at a plot diagram, we can see with quite a nice normal cluster around that. And the two faults are kind of isolated from each other. So maybe we're not doing a bad job here. But then when you apply your filters, this is where we hit the problem with the current methods. The instance on the left where you have quite loose thresholds around that, so you've been quite loose with how you've set them, you've given yourself some headroom in there, leads to less false alarms. So you'll see less false alarms coming through, but then you'll also see thresholds quite loose, you noise, but you miss a lot of genuine alarms. Now, if you take the other approach of taking a tighter threshold around those, your true alarms through, but you also generate much more noise. You're generating many more false alarms. Where the problem of just having thresholds per features comes in, you're always in this trade-off between loose versus tight thresholds, and either missing genuine alarms or alarms that you miss them anyway. And the third problem with this is the new type of failure that our current features that we've decided to pick just doesn't apply to anymore. It fits straight into it. This is the problem. This feature extraction and setting individual thresholds per feature really just leads to information overload, do not scale. If we're having to set a threshold for duration, a threshold for the mean power, a threshold for maximum power, also include the transformer at 10 Hertz, for example, or power in the middle of that swing while the temperature is less than 20 degrees and it's moving in a certain direction. Like is to constantly go through and tweak these features of finding that balancing point between false alarms and true alarms. So include all of them. And it's clear, hopefully, from what we've just said, that those traditional manual methods just do not scale. There's too much effort to understand the system, becoming an expert in that, potential parameters, not only for each asset, but also potentially for each direction. So this is the problem that we saw in the industry. We saw a lot of organizations monitoring their point machines in this way and hitting the problems that we've just described. What we work towards is really to leverage machine learning to take care of this for us, to automate that feature extraction, thresholding on our behalf, so that we don't have to be experts in the system and we don't have to manually define hundreds of parameters. So I often stumble across two main terms. We see supervised machine learning, where we train an algorithm against a known set of data and we produce a model for that. Now, we often find an issue in that, whereas there is not enough ground truth. So where we see a failure, we often don't find a of exactly what happened so that we can train an accurate model off. Across the industry, we just don't have enough labeled data. Not only that, point machines really fails. Actually getting the ground truth for that specific point machine is quite difficult. Unsupervised then, the machine learning, but don't apply any labels, and the machine learning model kind of automatic. And then from there we can see different separations between those classes. So we were at a decision point. Do we move towards the supervised or the unsupervised? And what our team have actually managed to do is make use of the best of use a mix of supervised and unsupervised learning when we're designing this out. So if we move back to that data that we looked at before, this is really what we want to do. We want to be able to take all of that data, all of our normal data, and effectively just draw a line around it and say, this is normal for us. This is how this point machine operates in a normal sense. 3D from here, depending on the number of features, that could be 3D, 4D, 20D. It would find out exactly what is normal for that point machine, which is the the largest of those buckets that indicates its normal behavior. Doing so, it's taken account for all of those parameters that introduce variability that we discussed before. So it's taken into account weather, it's taken into account the length of the point machine blade, it's taken into account that introducing some variability. And then further to that, it's also able to isolate points as well and group those into their own distinct buckets as well, so we can treat those separately. So let's apply this to the real world. How does this work? How does this theory work? Initially, we start off with a training phase where the algorithm effectively builds up an idea of this normal behavior. And that can be, depends really how much that point machine swings. We see anything from 1 day to, I think, a maximum of about a week so far. We kind of turn it live, and then into that live phase, the point machine continues to learn. It just builds up a better definition of normal, and then begins to flag when things aren't normal. So let's see that happen in real life. So at the very start, we have a few data points. The algorithm is just learning up, is learning what is. From there, we move it into the live phase where it's got that understanding of normal, kind of box around it. It's bucketed more swings together. And then as we get more and more data, it's continuing to normal, which then means when we get a fault, it can treat that separately and it can raise it immediately to the operator. Now, that part is the unsupervised part, able to separate out normal and abnormal movements. Now, what's really cool about the algorithm is once it pops up and says, we think you've got a fault, this point machine is deviating away from its normal state, it's able to ask the operator to say, what fault is this? And this is where the supervised part comes in now. So the algorithm will prompt the operator to say, do you recognize this? And the operator may look at the movement or get, yeah, that is a bearing failure or a dry slide show or whatever it may be. Be able to automatically categorize that for that individual point machine. So I now know that this is a bearing failure, so I can just include that in my notification so that the operator is better aware. And then maybe we get a third failure has an option. They can either say, yep, that is the same, it's another bearing failure, or it's a power drive issue. So you can classify this intelligent library of specific sim machine over time. And it's a much more effective way to treat issues than the previous threshold manner that we saw. So a little insight into, I guess, how the algorithm works, a bit of a deep dive into the data. Some of the benefits that we've seen from rolling this out across customers in a kind of better format. The algorithm can be specifically adapted to each individual asset. We know because of the variability that we saw at the start that that's really important. There is little initial training required, so you don't need to leave the algorithm running for 6 months, a couple of days, and then it really builds up its understanding of normal. We can include all of those features. We can have a large number of features that really actually describe the behavior of that point machine. And we can also classify as well some known failures. And I think the most important point on that slide is that the algorithm is always learning. It's always adapting. And that really reflects Tyrus as a service. We're constantly tweaking, we're constantly updating. Continuous improvement is really one of our and through that we can offer a smart, informed and efficient maintenance program for point machines. So final slide. What's the roadmap look like for Tyrus? I've talked to you today about points, and we're kind of all of our customers, not just the current select few as of today. And we've just launched AZLM, so axle counters. We got that available as a free trial. So if you're interested in monitoring axle counters, we can effectively ship you out a couple of the gateway devices, a couple of the sensors that we use completely free of charge. You can use it for 60 days, you can evaluate it, see the benefits firsthand rather than through PowerPoint. It's always much more powerful. And then we can move after that. Here we're introducing a really cool rain model for track circuits, and then we'll be advancing our axle counter capability as well. So hopefully that was informative. Thank you for the opportunity to present today. Happy to take any questions.
Mr. Murli, do we have any questions from the audience?
Sir, if there is no questions, I request participants, if there is any questions, you can please raise. Sir, we are having a question, sir. This is from PhD Sarvana Kumar. I will read the question. Since Tyrus platform monitors the CBT system, can we use it for mainline?
Sorry, could you just repeat the end of that question? The line broke up.
Monitors the CBTC system. Can we use it for mainline?
Our CBTC monitor to cell track system, the Thales signaling system. We can incorporate aspects into that as well in the future, but today tends to be.
So that's the question, sir. We don't have any further questions.
Okay.